Let's do basic multivariate analysis. One thing I should warn you is that univariate analyses didn't used to be called univariate analyses because there didn't used to be multivariate analysis. So if you read old papers, people don't know they were doing univariate analyses because they only became univariate when there was something to compare them to. In new papers, you will see anything like that referred to as a univariate analysis sometimes, but in old papers, they won't call it that. They'll call it other things, but not univariate analysis. Like, they'll just assume that this is analysis. Like whole brain group analysis or individual subjects analysis or ROI analysis, but they won't say that it's univariate because there was nothing to compare it to. Okay, and then we got multivariate analysis. Multivariate analysis is extremely awesome and saved fMRI. fMRI was dying under its own weight, and the discovery and invention and proliferation of multivariate analysis totally changed the world for fMRI researchers. It gave us at least 10 new years of life and maybe longer. And so, and it's such a simple idea. So I'd like to give you what the simple idea is and to try to give you a sense of why that totally blew open all of fMRI for everyone for a while. I don't know for how long, because it hasn't ended yet. Here's a brain. It's three-dimensional. Inside that three dimension, I've picked some voxels, which I drew in a picture. Those are some voxels. Everyone's with me? So that's a three-dimensional cube of voxels. Now I'm going to show you two ways of thinking about the activity of this brain region in those voxels, the old way and the new way. It took me 7 years to realize that this is the key intuition in multivariate analysis. So just so you know, this is not obvious as a feature of multivariate analysis. But I think once you think about fMRI data in the way I'm about to show you, everything else about multivariate analysis follows. Okay, so in the old way of thinking about analysis, once we got rid of time by converting to betas, right? So we had 4-dimensional data, then we solved for the betas, now we had 3-dimensional data. Everyone's with me? Yes? Okay, so in the old way of thinking about fMRI data, the axis is where the voxel is, right? And so if we had 12 voxels, we'd lay them out in a picture in space, right? So this is voxels, you know. And then we could look at the contrast value for a condition in each voxel, right? And so we might say, okay, here's, okay? So this is the univariate way of thinking about fMRI analysis, right? This is the way you think about it if you're asking the question where and how much. So if we label these, when you look at this way of displaying fMRI data, what you might say is, well, some places that seem to have a medium beta to both conditions. There's some places that have a strong beta to condition A but not to condition B. And there's some places that have a strong beta condition B but not condition A, right? And that could be like the ventral visual pathway, right? There's like V1 responds to all conditions, FFA responds only to faces, PPA responds only to scenes. Everybody's with me? Okay, and so this is the way of thinking about the relationship among voxels and their responses across conditions to answer the question where and how much. So now I'm going to take, so this is the univariate way. Now I'm going to take exactly the same data and I'm going to try to represent them in a different way. So right now I'm not doing anything, no analysis. I'm just going to draw a different picture of the same data. This picture is in 12 dimensions, but you can only see 3 of them. Okay? Do you believe me? Because it's really hard to draw in 12 dimensions. Condition A, the beta value in voxel 1 is medium. Voxel 4 is large, and in voxel 8 is small. Yes? Okay. Voxel 1 is medium, in voxel 4 is large, in voxel 8 is small. This point contains all of the information in that line. So the question is, did you follow what I just did? I turned this way of thinking about betas in space, I made that a vector. Now I made each voxel a dimension of multidimensional space. And so this vector became a point in the multidimensional space defined dimension is 1 voxel. Okay, I'm going to do it again. So this number, in voxel 1, it's medium. In voxel 4, it's very small. In voxel 8, it's large. So voxel 1, it's medium. Voxel 4, it's small. Voxel 8, it's large. So one thing that we lost in going from this view to this view is the relationship in space of the voxels. That's actually critical to understanding this. Here we had space. When we put it in this representation, we don't know the spatial relationships among those voxels. I mean, of course, we know them in the same way we knew them here, right? This is a representation, this is a representation. But right, there was a sense that when we looked at this, we could see space. When we look at this, we can't see space anymore. We have the three-dimensional structure of the brain we can no longer see, unless, for example, we happen to know that it projects onto dimensions 1, 2, and 3, and we could look at the projection of this in that axis, the axis defined by voxels 1, 2, and 3 as opposed to the others, and so on. We could get space back out. There's nothing spatial about this representation inherently. I know, so that's what I said, is I can't draw 8 dimensions. In fact, even 3 dimensions is really hard to draw. So I'm drawing 3 dimensions, but you should imagine 8 dimensions. If it's, so right, some people find the idea of 8 dimensions really hard to imagine, but you can imagine 4 dimensions, so just keep going, right? So if you're asking, really, 20,000? So usually for any purpose, we're going to pick a subset. And the question of which subset are you interested in is the problem of feature selection, and we're going to talk about that. So for now, again, we're going to temporarily assume there's some reason I picked these 8 voxels. And then if you could understand this representation of the voxels, then you can ask the question, why those 8 voxels? And that is a totally good question. How out of the 20,000 voxels did you pick those 8 is a very good question that we will talk about. Right? So there's 2 questions, as there was before. There's the question of where, which we're going to temporarily assume we've solved, which is the question, which voxels, right? And then there's the question of what are you doing with those voxels? And here I'm trying to give you just a different way of thinking about the data in the form of positions in the space of voxels. And so actually this is exactly like that. So there's going to be a question here of which voxels, which corresponds to the question over there of where are we looking, right? So we're going to have that same problem. So just like there, we could ask how much activity is in a group of voxels once we knew which group of voxels we were asking about. Here, we can ask questions about this representation of the data in some set of voxels once we know which voxels we're talking about, right? But again, I'm going to show you what we would do with that, and then we can ask about all the different ways you might select which voxels. And there's many possible answers to this question, right? And then once you've answered this question, so it could be the same one we started with. You could say the amygdala. So that might be 80 voxels maybe, right? So if you picked the amygdala, if you were interested in the amygdala, then you would have 80 voxels in the amygdala. And then the analysis you would do would be in 80 dimensions. Is that clear? And 80 is about, right. In typical applications, we're talking about 50, 80, 100 voxels. And so a 50, 80, 100 dimensional space. If these came from space, then voxel 1 and 2 are not independent. They're right next to each other, right? Probably some of the brain signal, some of the blood signal from each of them, not to mention you smoothed them, maybe you upsampled them probably. Voxels 1 and 2 are not independent measures of the brain. And so in this space, we don't have 80 independent dimensions. There's correlated structure in the data here. That is definitely true. And what you're going to do about it depends on a lot of things, right? So there's various things you might do about correlational structure depending on what kind of analysis you're going to do. And I'm just going to hold that thought. Because the key step I want everybody on board for is the idea that this representation and that representation are 2 equivalent representations of the same information in which we lost no information. As I say, that's the one insight which I think once you have that insight, then you can figure out everything about MVPA really straightforwardly. And actually, I think it took the field of fMRI about 10 years to have that insight, and once they did, everything changed. So this is not a trivial insight, but it's, I think, the key that unlocks the treasure, right? Once you know that you can think about fMRI data this way, then we can do tons of stuff. So I just want to make sure that everybody gets, you can translate from this representation to that representation. There are two different ways of representing exactly the same information. Haxby's first paper is in 2000. The first Haxe paper was 2001, which was widely ignored for about 8 years. The form in which he did this answer was not this as general as this. So I think probably for two reasons. One is that he is in fact using this intuition, but not overtly. That's the first thing. And the second thing is that machine learning was not as voracious. So the main thing that changed fMRI, right, is that, so this is the estimates of the beta values for conditions A and B in run 1, for example, right? We can do it again in, say, run 2, run 3, run 4, if we did 4 runs, right? Okay, now we have a cloud of data in a multidimensional space. So I think once fMRI data started to be represented like that, once gazillions of people were being trained in machine learning and had nothing to do with their time, then people who were doing statistics and machine learning for other problems saw fMRI data represented like this and were like, oh, right? Because all the ways we've represented fMRI up until here don't look phenomenally familiar if you've been doing machine learning for the last 5 years. But if you've been doing machine learning on whatever, like how long it takes an airplane to take off, or the shape of a kidney, or like the economics of Guinea, whatever it is, data look like this. And so tons of mathematical tools and techniques and solutions and just energy had gone into analyzing data that looked like clouds of points in multidimensional spaces. And as soon as fMRI data looked like that too, then everybody's like, oh, I have a huge toolbox I can apply to your data just like I apply it to any other data. And that is both the strength and the weakness of what happened next, right? Is that everyone's like, let's try everything. And you don't have to have even heard of brains. You could have been studying Guinea for the last 10 years, but you know everything you need to know because the data are clouds of points in multidimensional spaces. Who cares how we got them? Let's go, right? So suddenly there was a huge outpouring of creativity, of discovery, of energy, of new collaboration, and of completely, stupid confounds rediscovered in dumb ways, right? So everything that happens, you get a massive influx from outside of energy and skills and tools into a field. But for the most part, I would say this has been 95% positive and only 5% stupid. Because in fact, there is a ton of information in fMRI data that can be revealed once you think of it this way that had not previously been revealed. Information was there in the data. It was just that the old ways of thinking about the data were not sensitive to that information. And once you thought of the data this way and had the new tools that allowed, it really, truly broke open the discoveries that were possible. Which is, again, why I'm trying to get this representation into your head, because it was the change of how we thought about what our data looked like from thinking of it in space to thinking of it in the space of voxels that changed what was possible, and therefore what we discovered and claimed and everything. There's two things that naturally follow from thinking of the data this way. One of them is classification. So classification asks the question, if I do the best job I possibly can of trying to draw a plane between those two clouds of points, then the next time, now when you show me a new data point that I've never seen before, and I use that line to guess what condition it came from, am I right or not? That's classification. Two clouds of data. Now, draw a decision plane so that for any new piece of data, you have a prediction of which class it came from. Let's test how well that prediction works. That's, in brief, the intuition behind classification. That's one whole space of things you can do with data once you've represented them. And the second is instead of thinking just about classification, is to think about the distance between those two clouds of data points. And that can be especially interesting if you have more than two. Right? So now if you have 3 clouds of data points, this way of thinking about the data lends itself to the question, is more similar to A or B? By thinking of it as, is C closer to A or B? Representational space. So the 2 directions that MVPA has gone, again, we can talk about the details, but for everything that people do with MVPA, you can think of it as either a question about classification or a question about relative similarity and relative distance, or some combination of the 2. And those are the 2 things that were facilitated and empowered by thinking of the data in this format. What I was thinking of doing now actually is talking through an example where univariate and multivariate data analysis were applied to the same data set, and how the answers from those 2 complement each other, and what that is taken to mean by the researchers in a pretty simple case that I think will help make concrete these very abstract ideas. So exactly what happened, right, when we thought about the data as clouds of points in multidimensional spaces, is this vast array of tools became available, which include the knowledge that there's many different ways to think about distance. So there isn't distance in a multidimensional space like this doesn't have only one meaning. There's many possible meanings of distance. And so which meaning of how you operationalize distance, that's a choice. Yeah. So when people say Euclidean distance or Pearson's correlation, different ways of operationalizing the idea of distance in this space. Yeah. So I drew it as if there's only one meaning of distance, but distance is just like classification. There's many different things you could mean by classification. There's many different things you could mean by distance. And the power of this way of thinking, you can see what those different options are, because as I say, they've been well developed in other contexts. So for classification, we can talk about different ways of doing classification. Haxby style classification, which is the thing that got published in 2001, is a very simple form of classification. And then there's support vector machines and nonlinear support vector machines and various other things that make classification more complicated, and different kinds of generalization tests. So classification is potentially complicated, and distance is the same. There's many different things you could mean by distance, and many different things you could do with distance once you've computed it. And so again, those are special topics. We could go into each one, but the main thing for us is to see how they're related, they come out of thinking of the data in this format. Okay, I'm going to teach an example from Marina Bedney, who is a professor at Johns Hopkins and was my postdoc, and I just recently saw her give a talk, and it was a particularly clean and clear example of univariate analyses and multivariate analyses and how they are related to one another to make inferences about how the brain works. So I'm just going to teach you that. I actually don't even know if it's published, so it's just an example. There's a brain region in the superior temporal sulcus, gyrus, temporal gyrus, the left hemisphere of people. And what many different researchers had found in this region is that when people read like to run, there was a lot more activity in those regions than when people read sounds like the rock. Okay, that's just true. That's a result, not a hypothesis. That had been done many times and in many different ways, but imagine a simple univariate analysis. You have a whole bunch of verbs like to run, to kick, to jump, to roll, to sprint, to bounce, right? A whole bunch of verbs that have lots of motion in them, and you either read them or hear them or generate them, and we look at where there's a big beta in your brain, and then we compare that to the rock, the tree, the stone, the stick, the leaf, right? And we get the beta for listening or reading or generating those words. And we ask where in the brain is there a reliably larger beta for these motion verbs than these object names. And the answer is, well, there's a big region in left STG like that. And the theoretical question at stake was, why the difference? Is the difference because these are verbs and these are nouns? Or is the difference because these describe things that move and these describe things that don't move? I'm giving you a slightly simplified version of the history, but that's the basic question. Is this about what kind of, whether this is verbs or nouns, or is this about things that move and things that don't move? Okay. So to test that question, one thing that Marina did was an experiment with another set of verbs and another set of nouns. Nouns that move and verbs that don't move, right? So, for example, think, to wonder, to hope, to dream don't have a lot of motion in them. And tiger, the lion, the gazelle do have motion in them, right? Okay, so the experiment involved people seeing pairs of words and judging how similar they were. That's just to make sure that you're actually thinking about their meaning, drawn from one of these 4 classes. Verbs with motion, nouns without motion, verbs without motion, nouns with motion. Okay. The first thing that Marina did was, so we have every voxel in the brain, right? We have their time course. Build models. Okay, that's my model. 1 regressor per condition, per run. Yes? So there were 8 runs in this experiment and 4 conditions. So she ended up with 32 betas. Is everybody following? 32 betas per person, right? Per voxel. But then we can make those into beta images. So then we have 32 beta images per person. Anybody not sure why? We're going over this again to help make sure that everybody's on the same page. So please stop me if you're not following. Yeah? Okay. So we fit every voxel in the brain with these 4 betas for every run, for 8 runs, which gives us 32 beta images for each person, right? Next step is she fits all those betas, so she has all those beta images. Now she makes a contrast image. Here's the contrast image in this person, right? 1. And this contrast is for run verbs minus the rock nouns. Okay, so the question is, show me all the voxels in the brain, or rather, for each voxel in the brain, compute the difference in the betas for the motion verbs than the animal nouns. Actually, what she made was a T-map. She actually got the statistics. And then thresholded that and said, in this person, show me voxels where the difference between running and rocks is large relative to the noise in those voxels in this person, right? And so in that person, she found voxels in the STG, right, that pass her threshold. Okay, so she says, by definition, the voxels in the STG that show this statistical property are the ones I'm interested in. Because my question is about, what do those voxels do? Do they like verbs or do they like motion? And so this procedure is the answer to the where question, to the which voxels question. Is that clear? So this is, again, that's what's called a functional region of interest analysis, where you answer the where question based on a binary contrast in that individual's brain at some threshold. So for everything we're going to do now, in this person, these are the voxels we're talking about. Right? And in another person, we will do the same procedure, same contrast, but a different person. And we will also get voxels, also in the STG. Maybe a slightly different part of the STG, but also in the STG. And so what we're going to say is, this is where which voxels. And what we are going to call that is the STG region that responds more to motion verbs than object nouns for each person. That's not the only way to solve the where problem or the which voxels problem. That's just one way, right? OK. One question you might ask is, what if there was some voxels in this person over here and some voxels in this person over there, right? And so one thing we usually do is use some constraint that says it's only going to be counted as the superior temporal gyrus if it's in the superior temporal gyrus, for example. Right? So it's not just a functional condition. It's a functional condition within some anatomical constraint. And how you apply those anatomical constraints differs across labs and practical things. But so that brown line, the anatomical constraint, we usually apply, almost every lab applies that in some way, either formally or informally, either anatomically or in some other way. You say it's only the STG if it's the voxels in this person that respond more to running than rocks that are in the STG. And that's my voxels that I'm studying. Questions? Okay. For each person, we have a set of voxels. And then we ask the univariate question, how much? Right? So to ask that question, in these voxels, the first person, I get the average beta value, right, for all of those voxels, or the beta value for the motion verbs. Now we have 8 of those, remember, because there were 8 runs. So I'm going to average those together too. So in each voxel, I will average across the 8 runs. And then I will average across all the voxels within the set that I'm studying. And that will give me, for each person, one average response motion verbs in that person. This is double dipping at the moment. It doesn't have to be. But at the moment, I didn't specify that it wasn't. It could have been or not been, but the way I described it, it was. As you could say this is by definition. Of course, this is true, because that's the voxels I selected. OK. But that's not the theoretical question. The theoretical question concerns the other 2 conditions. Okay, so what Jaden's asking is, here running is high and rocks are low, but that's not a new discovery. I required that to be true of a voxel. I only included voxels in which I knew that would be true. So that doesn't count as a discovery. That was the question that Jaden. But that was not the question, right? The question that we were asking is, voxels that property, that like running more than rocks, what do they think about thinking in tigers? That's where the theoretical work is done. Yeah? And so in the univariate analysis, what that question means, when you're doing a how much question, is OK, what's the average to the other 2 conditions, right? If this is about verbs, it should be high to thinking and low to tigers. If this is about motion, it should be high to tigers and low to thinking. Everybody following? OK, that is the classic version of an fMRI selectivity question. And the data look like this. So if you ask the how much question, first averaging across runs within a voxel, then across voxels within a region, and then you get your statistics across subjects, right? So the variance I'm representing here is across subjects. Then what you say is, wow, this region responds a lot to running and thinking, and not a lot to tigers and rocks. It looks like it responds selectively to verbs, right? And so that kind of analysis led to 10 years of fMRI literature, where the question was selectivity. Is there a region that responds selectively to A, not B? And if you wanted to dispute that interpretation, you might think of another condition you would want to run, right? So the game was to think, well, what else is different between running and thinking versus tigers and rocks, other than that they're verbs, and you would think of things, and you would try that. And it was about having more and more different bars in this graph in order to figure out what is that profile about. And there were big fights about certain things, like what intermediate values mean, because of course you don't always get high or low. And one particular fight was about non-zero responses to control conditions. You found that it responded less to tigers and rocks than it did to running and thinking, but not actually zero. Then what should you make of that? Does that mean it likes verbs more than nouns, but also likes nouns, or not? And sometimes huge theories of the universe depended on the interpretation of the non-zero response to the control condition. Here again, the Canwisher-Gautier debate about the FFA is in part about a non-zero response to a control condition, where Nancy said the non-zero response to the control condition is not interesting. What's interesting is the really big difference between the control condition and the experimental condition. And what Isabel said is any theory of any region has to account for all of the responses, including the small but not zero responses to control conditions. So that was one of the philosophical debates about how to interpret data like this. Yeah? Okay. And so the question of selectivity was a question about the relative magnitude, or how much activity there was for the different conditions. These are average beta values with variance of beta values, but you can just look at that and say the variability of the betas, they're all above zero. So it depends what you think zero is. And this debate was mostly had in percent signal changes, so zero was slightly more meaningful. But yeah, there are definitely debates about if this is positive, is that theoretically profound or not? And again, there's a lot of assumptions there about what's rest, what's zero. Regions might deactivate. What if you found that rest was in the middle between your active condition and your control condition? When you see a brain region that does this, so that's if this is rest, and it deactivates a little bit for one condition and a lot for the other condition. In 2003, I published a paper in which I said data like that are uninterpretable because you can't tell whether that's a larger response to the blue than the purple or a larger deflection from rest for the purple than the blue. And then everyone else in my field was like, no, that's interpretable. Blue is larger than purple. Move on. I think that there's reasons to accept that conclusion based on how variable rest is, although that could be artifacts of how variably we operationalize rest. Basically, I moved on too. Yeah, so in Isabel's case, right, it was a debate about small differences from zero and from each other among the control conditions. How profound is that in interpreting the function of a region? Yeah. It also relates to philosophy and other things. Okay, so that's the how much question. That's a univariate analysis. And the question there is a question about selectivity. Error bars I drew are across subjects. So I repeated the procedure for each individual participant. I got bar graphs for each participant. And then what I'm representing for you is the average across participants and the variance across participants of the results of that procedure. In the multivariate analysis, you can take the same voxels, exactly these same voxels, and now, instead of analyzing them this way, averaging them, you can now use them to construct the multidimensional space of voxels, right? And within that space, we have 8 measurements. Okay. We have 8 beta values per condition per voxel. Yes? Is anybody confused about that? 4 conditions. We fit the 4 regressors to every voxel. So we have 4 betas per voxel. 4 conditions, but then we had 8 runs. So for every condition, we have 8 beta values, 1 per run. in every voxel. Yes? Okay, so then we can re-represent the response to these 4 conditions as a cloud in each subject's ROI, where the dimensions are the voxels of the ROI, now more like 80 dimensions, because voxels are, ROIs are around 80 voxels big. 80 to 150 would be normal, sometimes more. So the size of this space, the number of dimensions could vary across subjects, because the number of dimensions is the number of voxels. Yes? Okay. And so what Marina did in this case, actually, just leave one out, with 7 beta values per subject. She drew 2 classification boundaries. The best guess classification between rocks and tigers, and the best guess classification between running and thinking. Now, this is SVM classification, which is one way of doing it. Between nouns and verbs, we know for sure we can classify, because you can see even just the average activity can classify. And so on average, all of these blue and brown ones, a different part of the space than all of these red and purple ones along at least one dimension, namely the one of the average magnitude. And so we know we're going to be able to classify those. Are people following that? We know those are in 2 different parts of the space because the dimension of average magnitude differs across them. So this is a line, a plane best separating rocks and tigers. And this is a plane best separating running and thinking, right? So we know you can classify nouns from verbs. The new question is, can you classify nouns from nouns and verbs from verbs along this other dimension, right? Now, if you look at the univariate response, there's no difference in the univariate response to rocks and tigers, and no difference in the univariate response to thinking and running, right? So the average magnitude of response to all verbs is high, and to all nouns is low. The question is, what about in the pattern? So why would there be a difference in the multivariate analysis if there isn't a difference in the univariate analysis? So we know when there is a difference in the univariate analysis, you could see it in this kind of multivariate analysis. But when there isn't a difference in the univariate analysis, it's still possible that there is a difference in the multivariate analysis. And that's because of what a multivariate analysis is. So this shows you what is the power of a multivariate analysis. And that is that it's not only sensitive to the shared average magnitude of all the voxels, but also to the relative difference between voxels, right? Whether one is relatively higher or relatively lower. Try to give an intuition for this. In 2 dimensions, try to give the intuition. I know there's a way to draw this. Here the idea is, right, that if you look at the average response in voxel 1, average response to the purple condition is that, and the average response to the pink condition also high? Yeah, thank you. That was right. Okay. Look at the average response on voxel 2. They're also very overlapping. Okay? So this is the key intuition, that if you have data clouds like this, they can have the same average response in voxel 1 and the same average response in voxel 2, but still be very separable. One simple way to think about this in fMRI terms is that there's a separate independent factor driving the whole region together up and down, which is often noise, right? And so one thing that's going on is there's noise driving the whole system, which is big. And then there's a small relative difference between the voxels. And the small relative difference between the voxels would be very, very hard to see if you looked at each voxel independently. When you look at the relative activity in the 2 voxels, then their shared variance is not as important. What you're looking is at the relative difference between them, right? And so in this case, the pink cloud is relatively higher on voxel 2 than voxel 1 compared to the purple cloud. And so that relative difference between the voxels is more informative for telling the difference between the colors than the absolute value on either voxel alone. And that signature, that the relative value is informative when the absolute value is not informative, is the information that multivariate analysis brought us that we didn't have before. Right? The relative information. So in this case, say we know that the average response to the motion verbs and the non-motion verbs is the same. Maybe the relative response in different voxels is nevertheless informative, even though it's hidden under big shared variance from trial to trial. That's one way to think about it. Another way to think about it is, if the neural populations sampled by voxels are slightly different from voxel to voxel, then there's a stable, meaningful difference in which voxel is relatively more responding to the different conditions. Right? But again, that difference we would expect to be small. So if the neurons that are more, so this is thought about, for example, with orientation. You can think of it in this case, whatever the features that distinguishes thinking verbs from running verbs. If there's intermixed neural populations that are just sampled slightly differently, then the difference between the two voxels in terms of which category they prefer will be a very small difference compared to the huge difference between what all neurons prefer to what they all don't prefer. And so multivariate analysis gives you a way to be sensitive to those small relative differences, as well as being sensitive to the big shared differences that are shared by all the voxels in the surrounding area. Okay, and so that's a neuroscience-y way to think about this. What mathematicians would tell you is, of course, when you look at something in a multidimensional way, there's more differences that you can detect than when you look at it in one dimension, right? If something is many-dimensional and you compress it onto one dimension, of course, you're going to be less sensitive than if you leave it in multiple dimensions. So mathematically, you can see this as necessary. Of course, it would be the case that multivariate analysis would be more sensitive. But if you want to think about it from the perspective of the brain or the MRI data, you can also think about why there might be information in the relative responses that's hard to detect by treating each voxel independently in terms of its absolute response. Right? And this is the standard picture everybody draws to make that intuition clear, right? Is that if you looked at the response in voxel 1 and the response in voxel 2, you would get that the two are the same. But by looking at the relative response in voxel 1 versus voxel 2, you get that they're completely different. Yeah? And so in this case, what Marina found, again, she used 7 betas out of 8 to draw those classification lines, then took the left out ones, plopped them down, and asked, does this line that I drew based on the other 7, does it do a good job of predicting for the left out one, whether it's rocks or tigers, whether it's thinking or running, or some other verb in that class. Now you get accurate, where chance is 50%, right? Because these are binary classifications. So I give it 1 new beta, right, in multidimensional space, right? And I say, what condition do you think that beta came from? And it guesses. Okay, so what she found was that verbs, this in each individual participant, right? This space is the multidimensional space of the voxels and the ROI in the participant. So you get a classification accuracy per participant, leaving each run out once, so you do it 8 times. You get a classification accuracy per participant. That gives you 1 number. Then you do that once for each person. And so this is the average, and this is the variability across people, right, in the classification accuracy. For verbs, in this case, we used individual subject functional ROIs to do feature selection, right? So we picked the voxels by this criterion, that they're the ones that show this univariate signal. Right? Then we asked the selectivity question based on univariate analysis, and sometimes called what is their information about, right? What code? What Marina said based on all of this is there is a brain region in the STG of each person, and that region responds more to all the verb categories than all the noun categories. And the pattern of activity in that region has more information to distinguish between verb categories than to distinguish between noun categories. And therefore, this is a brain region selective for verbs. It contains information relevant for distinguishing among verbs. And when you put a package together like that, it feels like it's getting very close to the core questions of cognitive neuroscience, right? Namely, where in the brain is which information processed or extracted? And so because of the possibility of that telling a story like that, and because it turned out, as an empirical matter of fact, that MVPA was often sensitive to stuff, that's part of why people got so excited about MVPA. So very often it turned out there was information relevant for discrimination conditions. Couldn't tell the difference between in a univariate analysis. And this particular pattern, where the brain region that responds most to a condition also distinguishes best among subclasses of that condition, feels particularly like a clue to something real. If you believe in regions, like stage-wise processing, if you think there are areas that extract information for particular jobs, then a pattern like this is like what you were most hoping to find, a convergence between the selectivity of a region and the information that it contains. That does not always happen, not even mostly. But when it does happen, it feels exciting. Thoughts? So the question was about overfitting. And so the simplest answer is the procedure that I showed you about, which is features are selected based on an independent criterion, and classification is on left-out data that is totally independent from the data that were used to define the criterion. And statistics are on independent repetitions of that procedure. So in that case, the chances of overfitting are low. That's a pretty good way of preserving the independence of multiple samples. But there's a big conversation happening about many other applications of MVPA that don't look like this, in which either the selection of the voxels or the cross-validation procedure is not as independent as the one that I drew, and then overfitting can be very possible. So that has definitely, that's a live debate because there are proliferating versions of MVPA, and this is only a very, very simple example. As the methods of MVPA are proliferating, questions about which of them might lead to bias or overfitting is a very live conversation. In this analysis that I showed you, the ROI was per subject. There are many ways of mixing and matching that can lead to inflated statistics, but that way we use one independent criterion to set the voxels, a different set of data to fit your classification, and a different set of data to test it, and then the statistics are across independent repetitions of that in different people. That's a pretty safe procedure. I'm going to do a few more topics in multivariate MRI analysis now, and then stop. And then this will also give you a chance to reflect on what you would like me to do tomorrow. So either I can just go through some of the topics that were in the list that were popular, but also you can think again, and either we can redo the survey or you can email me. We can think about ways to, now that you've seen all of this and what it's like, change your opinion of what you want me to talk about tomorrow. First topic. In this version of multivoxel pattern analysis, we assumed that we knew which voxels we wanted to study in some other way, right? So we considered the version where we wanted to study the amygdala, and we used anatomy to select them. We considered the version where we wanted to study this part of the left STG, and we used a functional localizer to select them. So in all those cases, we assumed that the question, which voxels, is solved outside of multivariate analysis. And what we're asking the multivariate analysis to do is tell us how much information or what discrimination or what can we classify in those voxels, given that the question which voxels was already solved, right? Yes? Okay. So one thing that you might see or you might want to do is the version of multivariate pattern analysis, which is most similar to the whole brain group analysis we did in the univariate case. That is where you want to know where there is information that can be used to do some classification problem. So again, here, this is where are there voxels that have a higher response to A than B, right? That's the group analysis whole brain version of a univariate analysis. There is a group analysis whole brain version of a multivariate analysis, asking the same kind of questions that we were asking before, but now not about a univariate difference, but about the pattern of information. Okay, so that's the first thing I'm going to talk about. So a priori feature selection is one option. This is a different option, which is usually called a searchlight analysis. So this is equivalent to, or analogous to, the univariate whole brain group analysis, now in the multivariate space. How this works. Okay, so feature selection is the word in multivariate analysis for the where or which voxels question. So the question that was called like picking your ROI or which region are you studying. When fMRI analyses, when cognitive neuroscientists invented the vocabulary, we called it region of interest identification. Machine learning people in their own world had defined a similar kind of problem, which they called feature selection, which is similar in the sense that out of the whole brain, we're going to choose some voxels and study them, right? That's the same thing we're going to do. Out of the whole brain, we're going to pick some voxels and study them. But in machine learning, that was called feature selection. And in cognitive neuroscience, that was called other things, usually like region of interest and identification or something. There are other differences, like in the traditional cognitive neuroscience case, you were then going to average them, right? Whereas in the multivariate analysis, you were going to keep them independent and use them as the space in which you then defined a classifier. So, but that difference then got collapsed, right? So now we could select voxels and then keep them all separate and do a classifier in them. So now voxels became features, right? And so the choice of which voxels you were analyzing is the feature selection question. And you can still use all the same old tools that we used to use for selecting features, but now you can use new tools as well. So there's other ways of doing feature selection that we didn't used to do that you can do now, that you think about it in these ways, on top of all the old ways. Yeah, so maybe what I should do first is talk about the features. Which voxels are we using, right? Which are this 1 to 12, where did it came from? Jen asked me that question earlier. And so standard options apply, right? The old option, it could be anatomy, right? Like the amygdala. I take all the voxels that are inside the amygdala. Those are my features. That's one option. Function. I take all the voxels that respond more to faces than scenes in the fusiform gyrus. That's another option, right? That's an ROI. A third option, in 2, the old way that we did this, we would say, in the fusiform gyrus, give me all voxels passing some threshold. That was usually the way we did ROI analysis, as a matter of practice. That was the habit. But another thing you could do functionally that's pretty similar is say within the fusiform gyrus, I want to pick some number of voxels where n is a constant. And so this is, there's 2 properties here. This one was contiguous regions. Okay, so the old way was we picked contiguous regions, often all the voxels that were all spatially contiguous and that had a large response in a contrast, like faces over scenes. Another option is pick a number of voxels, like 100, that differentiate between conditions, but you don't care in which direction, right? Here it was voxels that respond more to A than B. Another option here might be that distinguish A from B, but I don't care in which direction. Or that respond to either A or B or both, right? So here, option 3 is a generalized version of option 2, right? Which is just, you could use some property of the voxels to decide that they're not noisy, right? That they have meaningful signal in them. And then study those voxels. I guess I should make this a 2x2 design because they were treated as correlated variables, but realistically, they're not. So anatomy, we're going to say function, and then here's options.